My name is Brooke Peterman, and this is my Lab 5 on Faraday's Law. In this lab, our main goals are going to be to explore the results of dropping a magnet through a conductive aluminum tube and to create a computational model of this interaction. We're also going to compare our experimental results with our computational results. The physics concepts covered in this are Faraday's Law, which is a change in magnetic flux through a loop area induces an EMF across the loop, and also Lenz's law, which says that the magnetic field generated from the induced current is opposite of the charge influx through the loop, which is the negative sign of the equation above. We're also going to need to know the magnetic field of a dipole and the magnetic force on a wire. For the experimental lab, I first started by marking north on the magnet. I used my magnetometer app on my phone and from lab 3 to find north on the magnet and marked it with tape. Next, I set up the experiment. This was kind of hard to maneuver with only two hands, so I set my phone up on my desk to record it. But I had a vertical tube with the magnet hanging above with north facing down, and then recorded each trial on my phone. So I recorded 5 trials of the time it takes for the magnet to fall through the tube. My data can be seen to the right here. And this phenomenon is that when the magnet enters the conductive tube, the magnet slows down and appears to be resisting gravity. And then the other data that is going to be necessary to do the computational model is that the mass was 0.023 kilograms and that the length of the tube was 0.3 meters and the width of foil was 0.05 meters and the inner radius of the tube was 0.025 meters. For the computational model, I started off with the starter code, and then first I changed my initialized conditions for length, width, radius, and mass. Next, I made an equation to compute the magnetic field of B, and then an equation to compute the change in flux throughout the tube. Next, I found the magnitude of the magnetic force on the ring using the equations previously mentioned. And then I also made vectors for the gravity and magnetic forces, and finally finished off by updating the magnet's velocity and position. I then ran the code. You can see here my final velocity versus time graph, as well as the bar magnet after being dropped through the coil. My final computational time was 0.311 seconds, which compared to my experimental time was 0.1 seconds longer. In reviewing my computational model, I found that the color that corresponds to clockwise current would be red because the north end of the magnet was pointing downwards as it fell through the tube, so there was a greater magnetic flux in the downwards direction through the loop. This means the induced magnetic field will point in the opposite direction as the magnetic flux, so the induced magnetic field will point upwards. So the induced current is counterclockwise. Since the bar magnet was red after running our experiment, this means that the red corresponds to counterclockwise and blue corresponds to clockwise. If I were to flip the magnet around, the velocity and position of the magnet would remain unchanged. And in comparison to our experimental system, the computational system was around 0.1 seconds off, as previously mentioned, and this could be accounted for because my hands might have insulated the aluminum slightly to make it go faster through the tube. To account for this in the computational model, we could have added additional forces against it. And the shape of the velocity versus time plot tells us that the exponential decay of the graph represents the magnetic force up slowly getting larger as the gravitational force down also gets smaller. In conclusion, I can now say that the resistivity of the conductor, if it were reduced as close as possible to 0, would cause the induced current to approach infinity because I equals V over R. The magnet would then take infinitely longer to fall through the tube because of the equation below. If there were holes or slots cut into the tube, that would affect the current because the ring currents would decrease due to the decreased loop area for the magnetic field to permeate through. Thank you so much for watching, and I hope you have a good rest of your week.